Okay, so I'm going to try and finish with, at the end, the proof of an important theorem that the wavefront set of a solution is contained in the characteristic set. Okay, and then I will pose some open problems for you. So where did we stop? So I said that if you have a C1 function, it can also be a distribution, okay? Then we will see that it will be convenient to write the differential of G in terms of one forms which are closely connected with the vector field we are studying. So namely, so mk of G, differential zk, and then there is a coefficient of dt, which is Lg minus mk of G, Lzk, k1 up to m, dt. So let me remind you, the mk are vector fields, unique vector fields. They are unique, actually, with this property. So they are a dual basis for the differential of Zj, these one forms. And L is d by dt plus aj xt d by dxj. And for now, I am assuming that L has only C1 coefficients. And the zk have the property that they are equal to xj at time t equal to 0. And they are almost solutions. Approximate solutions is what we call them. So at t equal to 0, they vanish to infinite order. Okay? So in practice, we study vector fields where you can actually find solutions Zj satisfying this. So if Lzj equals 0, it simplifies this. You see, this part will be 0, so differential of G will be expressed in terms of dzk, where these are the coefficients, and the coefficient of dt is Lg, okay? And one can actually form a differential complex and study, just like the Doblov complex, the Dipart complex, one can study the solvability at different degrees. But that's not what we are here for. Okay, so now, so this is proved by just applying both sides to the basis of vector fields L, M1 up to MM, which is what I did. Okay? So this is a basis of vector fields in X and T space. And so this, let me call this star. So because of star, if I apply the exterior derivative to an M form of this type, dz1, dzm, okay, no dt, then of course this will be dg wedge this, dg wedge dz, dz will mean all these things, okay, so this is dz, and using this then, this becomes, well, this part wedge dz is 0, so I only get this part, right? So I get Lg minus mk of G, Lzk, k1 up to m, dt wedge dz, okay? So this is an m plus 1 form. Okay, so that's what I get, okay? This is going to be really convenient now when I try to estimate the Fourier transform. Let me see, let me try to find a better, okay, this is better. So now I'm going to take a G, which basically is the integrand in the FBI transform, basically with some parameters. So from now on, I will use this notation for these functions, okay, this vector valued function, z. Now I will use C and S as parameters, and I define the following. E depends on S, C, X, T. By definition, it equals I, square root of minus 1, that is, IC dot S minus Z of XT minus norm of S, and then the square of S minus Z of XT. The square of a vector means the sum of the squares of the components, okay? Now, what is this thing? Where that? Notice that you see, note the following. At time t equal to 0, at time t equal to 0, what I get is EIC dot, when t equals 0, Zj of x0 is xj, so Z of x0 is just x. So this is S minus x squared. Well, these are now real valued, so I can just write this, which is exactly the exponent you see in, of E in the FBI transform, okay? Okay? So what I'm doing is I'm perturbing that, okay? That, because you see, to estimate the FBI transform of a function, I'm going to integrate by part. I will go to a level t, okay? And so there will be an integral and with this, and an integral with this, and then in the middle, by Stokes' theorem, there will be a double integral, okay? Now, that double integral, in the double integral, I'm going to use the fact that I have a solution. I have a solution, and that will allow me to estimate that the double integral, okay? Now, what I want to estimate is the FBI with this. Now, I choose a convenient t where I exploit my assumption. There is an assumption. Remember that the imaginary of A inner product C is negative. I use that to show that the integral, when this is the exponent, decays nicely, okay? So I'm going to go through the details now. Okay, so let B be a small ball containing the point we are looking at, x0, which we call 0, okay? And psi, a smooth function of compact supports, supported in B. Psi, let me see if this works. Psi is identically, identically 1 near 0. Okay, so psi is, this is B is a ball in X space. So psi is a function of X. Okay, and now I'm going to apply this to the following function G. So apply double star to the function G, which is, it's a function of X and T with parameters S and C. So the function is psi of X, f of xt. Remember, f was my approximate solution. F was my approximate solution. So for example, it can be a solution. But I told you that it doesn't necessarily have to be a solution. I'm proving a more general result here, in other words, okay? So psi, okay, so apply this to G equal to this times E, so here comes the exponential, to the power of E S C X T. So apply that. Okay, so when t equals 0, it is the integral of this that I have to estimate. That will give me the FBI transform, remember? Okay. Okay, so here with S and C as parameters. So apply double star. Double star was taking the exterior derivative. So you are taking the derivative in X and T variables, okay? S and C are just parameters. So I get star prime. So you get star prime, which will say that the differential of G, dz, remember dz is an M form, dz1 with dz2 up to M. So if G is this, then that thing told you, you take L of G, L of this whole thing, okay? And L of this, so use the product rule, blah, blah, then you get L of psi f plus psi f times LE minus the sum k, 1 up to M, mk of psi f plus psi f times mk of E, and this multiplied by LZK, and everything multiplied by e to the power of E. Okay. Now, by Stokes' theorem, here is what here is where I use this Stokes' theorem in this region, in this domain. So this is in X space, this is in T space. So I'm going to take a cylinder, so this will be the ball, say. And here I will be at a level T1, say. This is the ball cross T1, okay? So this is the ball cross time T equal to 0. Okay, I'll choose an appropriate T1. Okay, so in any case, Stokes' theorem tells me, so by Stokes' theorem, the following certainly is true, namely the integral over B of, now this is, I should have said, yeah, okay, that's fine. The integral over B of, so at time t equal to 0, put t equal to 0, okay? So you get g of s c x0. At time t equal to 0, the zj are xj, so dz1 wedge dz2 blah blah just becomes dx, okay? That equals the integral at time t equal to 1. At time t equal to 1, the form dz1 dz wedge blah blah just becomes the x takes the Jacobian with respect to x of z and evaluate at time t equal to 1, okay? All right, plus now there is a double integral. Okay, so the double integral from 0 to t1 over the ball B of the differential of gz, which is given by this. Okay, so it's given by this. This is what I want to estimate. This is exactly, this is, you see, this is equal to f psi of x, the cutoff function, times the trace of my function, times 0, e to the power of I c dot s minus x minus c s minus x squared dx. In other words, it is the FBI of my function psi f evaluated at s dot c. Okay, the FBI of this function. That's what I want to estimate. I want to show this has the appropriate decay. An appropriate decay in a conic neighborhood of C naught. That will mean that, okay, so that C naught is not in the infinity wavefront set of f of x0. Okay, so I'm going to estimate this by estimating these two. Okay, so let me see which one I want to estimate. Okay, let me estimate this. Okay, I haven't used the fact so far, the hypothesis, and I haven't used this. Well, I haven't used anything in the hypothesis so far. Now, so since the ZJ are approximate solutions, meaning LZJ of xt is O of t to the k for all k, okay? So you plug L is d by dt plus blah blah, Zj is xj plus t times phi j. What that will mean is this will give you easily, if you apply it for k equal to 1 already, it will tell you that phi of x0 equals minus a of x0. Okay, where a is the vector of coefficients of the vector field L, okay? So this is pretty easy. Now, so, and then using the assumption, this means that the imaginary of phi of 0, 0, inner product C naught is negative, because the assumption was the imaginary of this dot C naught was positive, okay? Using the hypothesis, this was the hypothesis. Okay, one of the hypotheses. Okay, and that therefore, you see, this means that after shrinking the ball B if necessary, after shrinking both the ball B around 0 and the number T1. After making T1, what this will give you is that you may assume imaginary of phi, by continuity, xt. And then, this is a conic thing in C. So it will tell you that this thing is less than or equal to minus some constant times C for all x in B, and T like this, T between 0 and T1, and C in a conic neighborhood of gamma. So gamma, a conic neighborhood of C. All right. So now to estimate, as I said, this is what you want to estimate, so I'm going to estimate this and this. To estimate this, you see, so G, remember, what is G? G is this. So these are bounded functions, so all I need to estimate is this, which means I need to estimate the real part of E. So at time t equal to T1. So let me figure out what that is. So the real part of E at any time, okay, well, you have the formula for E, so compute the real part of E. Okay, so it becomes T times C dot the imaginary part of phi minus norm of C S minus X minus T, the real part of phi squared minus T squared, the imaginary part of phi squared. Okay. Now let me call this a star prime. So you see, this part is less than or equal to minus a constant times C times T already. Okay. All right. And, well, this part could be harmful. If this quantity is less than this, it could be harmful. Okay, it could be harmful. But the thing is this. If I choose S very small, and X small, so shrink the ball B, okay, then the T appears with a square, so it's going to be smaller than T, and here the T appears with a square, so therefore this is going to be dominated by these parts. Okay, so after contracting B, okay, so and so what I get is for T1 and B small enough, but B always a ball around 0 enough. This implies, or star prime, this implies that the real part of E, S, C, X, T is less than or equal to minus C1 norm of C, T. And so therefore, you see, this part has exponential decay, but of course when T is positive, when T equals 0, I don't get anything, it just says it's bounded, okay? But in particular, at time T equal to T1, I have an exponential decay. And therefore, you see this, this thing decays exponentially at time T equal to T1, okay? Okay, good. Okay, so let me write it. So therefore, the first integral on the right, g of S C x T1, the differential, this M form, this decays, let's see, C1 prime, E minus C2 prime, say norm of C. But for all C, remember, in a conic neighborhood. Okay, that's where this was valid. Okay? All right, now comes the estimate of this double integral. And this is where you'll see why it is very useful to write a one form, not using dxj and dt as one usually does, but rather using these forms, the dzj and the dt, which are the ones that are really adapted to the vector field L. Okay? So let's see. So to estimate this, the differential of this was equal to this, okay? And so I have to estimate the double integral of each of these terms, okay? So let's say, since it's really, so when you take L of psi f, you get two terms. So let's see that, for example. So we'll just look at some of the estimate for some of the terms, and the rest will be the same. So one of those that arises is, say, psi times LF, and then there is e to the e, okay? So you have e to the e, otherwise dz dt. Okay, well, LF, remember, f was an approximate solution. By the way, if f were a solution, I wouldn't have to worry about this, okay? I still would have to worry about f times L psi. But psi is supported near the origin. It's constant near 0, so L psi is 0 near the origin, okay? And if you are 0 near the origin, this part will already give you an exponential decay, okay? So in any case, what do we do now if all we know is that this is an approximate solution? Okay, let's see. From the exponential, what do you get? This is the decay you get. E minus C1, norm of C, T, okay? Okay, now, LF is O of T to the K. Okay, so you have to deal with this kind of integral, okay? This is good when T is positive, but, you know, T goes up to 0. When it goes to 0, it doesn't help me. But this is going to help me, namely the following. E to the power of something, e to the power of something is always bigger, less than or equal to, I mean, e to the power of a negative thing, is always for any k, this is less than or equal to something like this, c to the k, t to the k. So you see what I mean? For a number a positive, right, when you look at the Taylor series of e to the a, so that means that this is less than or equal to a constant, in this case k factorial, over a to the k, right? That's what I'm doing here. This is less than or equal to this. Okay, now 1 over t is bad, as t goes to 0. 1 over norm of c to the k, that is good. That's what I'm looking for any k. But now, you see, you have this that saves you. You have this that saves you. The fact that this is an approximate solution. So in other words, it doesn't have to be a solution. And so the t's that way cancel out, and I get my decay for any k. Polynomial decay. Is that clear? That's what happens for each of the others. LZK is also, remember, an approximate solution, so that takes care of all of this. LE, let's see E. What is E? Well, if you look at E was written in terms of quadratic polynomial in Z. Well, the Z's are approximate solutions, so the quadratic polynomial is also an approximate solution, okay? So LE is also O to the K for all K, okay? So, therefore, I get a polynomial decay for this also, okay? So, therefore, the double integral also behaves like this. For any case, there is a constant such that this happens, okay? But again, for all C, because I use this for all C in my conic neighborhood. Okay, so this part decays exponentially, this decays polynomially, therefore this decays polynomially. But this is the FBI transform, it's not the usual Fourier transform. The wavefront set was defined using the usual Fourier transform. Well, it turns out the usual FBI also characterizes smoothness microlocally. To show that, use the idea of using these almost analytic extensions that I showed you, okay? The details are again in our book, okay? And so this proves it. This proves, so what have we proved under the hypothesis of the lemma? Under the hypothesis of the lemma, which was that the imaginary part of A dot product C naught. So if this, which ended up being minus imaginary part of phi, if this is positive, this implies that this function of x, so at the origin, this direction is not in the wavefront set of this function of x, just this function of x. Okay? Now, if L were real analytic, okay, if the coefficients A were real analytic. In that case, the Cauchy-Kovalevska theorem tells you can find this Zj, okay, very easy. And then in that case, what that means is that this integral will also decay exponentially, because you won't have to worry about, you see, this part will be 0, you have the zk, okay? So this will, the double integral will also decay exponentially, this will also decay exponentially, which means your conclusion would be that it will be a stronger conclusion, that this is not in the analytic wavefront set of this, okay? So more generally, L doesn't even have to be real analytic. More generally, so remark. Two things. If, first of all, L is not just an approximate solution, but a solution, and the LZK were actually 0, then we have the steps, these steps prove that this is not in the analytic wavefront set. By the way, we have also, let me say, from what we did this morning, the C-infinity wavefront set of any function is contained in the analytic wavefront set. You know, something that you'd like to see, you know, I mean, if a function is analytic, it's infinity. What I'm saying is if it's microlocally analytic, it should be microlocally smooth. How does this follow? Well, what did I prove this morning? I showed you that analytic wavefront, if something is not in the analytic wavefront set, then U is the boundary value of certain holomorphic functions in certain wages. If it is a boundary value of certain holomorphic functions, it is a boundary value of almost holomorphic functions, and so therefore C naught is not in the C infinity wavefront set. Okay? All right. Now, let me state the theorem then, the theorem that I've been after, and the proof will be short. It will follow easily from the lemma. There is just a trick. The trick due to Francois Treves, who was my thesis advisor. He's still alive. He's about 94 years old. Okay, so now, okay, so here is the theorem. Okay. So this time, L will be C infinity or real analytic, we'll see. Let L be like this, so it will be at least C infinity. Okay, you don't actually need it to be C infinity for some purposes, but in any case. Okay, now actually, let me take it to be C1. Okay, let me take it C1. Okay, now I make the following assumption. First, for each theta, a parameter in 0 to pi, I'm going to define a new vector field, L theta be d by ds minus e to the power of minus I theta times this vector field L. So this involves differentiation in x, t, and s. So I have added one more space. This is the way to look at it. In the lemma, we had a vector field in x and t, and so our space was, you had x here, you had t. Now in this theorem, the setting is the x and t, I view them as x. The x and t will play the role of x before, okay? And the role of t is played by s, okay? S is, you see, so d by ds is behaving like this, d by dt here now, okay? All right, now I make the following assumption. I make an assumption about existence of approximate solutions for this now, the analog of the zj. Well, before I had zj, which at time t equal to 0 were xj. Now I need zj, which at time t equal to 0 are not only xj, but I need one more, which at time t equal to, no, time now is s, sorry. I need zj, which at s equal to 0 equal xj, and z, which at s equal to 0 equals t, okay? So here I had m functions, now I need m plus 1 functions. So I'm going to assume those exist for each theta, because for each theta, these are different vector fields, okay? Let me again say, if the aj are C infinity, one can show they exist, okay? Using this idea of Borel, okay? It's the same as trying to show that almost analytic extensions exist for any smooth function, okay? So So assume that for each theta, there exist C1 functions. So this is the same kind of assumption as before. So let me call them phi1 theta. So now these are functions in XTS, phi m theta, XTS. Yeah, I need m plus one of them, but I will come to the last one in a moment, such that Zj theta of XTS, which are Xj plus S phi j theta of XTS, are approximate solutions in the sense that they are flat at s equal to 0. So these functions satisfy, yeah, pen, okay, yeah. Let me see. One can find one. Okay, let me see. Maybe I might find something that has been used. Okay, let me try this. Such that, okay, L theta for this vector field, if I take these functions, these are approximate solutions, but in this sense, okay, flat. Okay? So before in here I had Z1 up to Zm. Now I am looking for each theta. I'm looking actually for m plus 1 solutions, because there are m plus 1 coordinates here when s equals 0. Okay? So what is m plus 1? It will be very easy actually. It will be like, so in addition I add, so let the m plus 1s theta be simply ei theta. Okay? It's just a constant. And therefore Zm plus 1 theta of XTS would be T plus S times ei theta. It's very easy to see that, in fact, you see, I want it to be an approximate solution. Well, in fact, this is a solution for L theta. You see, if you apply this to this, d by ds gives you e to the minus I theta, then minus e I theta. L of this is 1, L of t is 1, so you get 0. Okay? And moreover, at time s equal to 0, I wanted to capture the one. So when s is 0, I get t. Okay, so I have captured t also. So I have the xj at s equal to 0 and the t. Okay, so this is exactly as in the lemma, except I jacked up the dimension, one more dimension. Okay. All right. Now let us see what the hypothesis, this hypothesis, what the corresponding thing is for this new vector field. Okay. Okay. Yeah, I will have enough time to finish the proof. In fact, I don't even need to rush. Okay, so it turns out that so before we were looking at imaginary of phi. Now it turns out that, you see, so I have tau c. So if I look at the inner product of, so if I take a c tau in Rm cross R, okay. So if I take c tau and take the inner product with the imaginary of phi sub theta, how am I writing my phis? My phis are var phi take phi sub theta at the origin. Okay, so you can, so before using the fact that the zk were approximate solutions, I told you that imaginary A was imaginary phi, and likewise here using the fact that the zj are approximate solutions, what you will get is this thing will equal, let me just write, will equal c imaginary phi, the phi of the previous lemma. Okay, times cos theta plus tau minus c real part of phi sine theta. Okay. All right. Well, look. Let us look at the characteristic set of L. What is the characteristic set of L? Characteristic set of L. Well, what is the symbol of L? It is tau plus aj xt cg. J. Okay. So characteristic of L, say at the origin. So when xt here 0, so at 0 cg. Okay, so let me write this as tau plus a of 0 inner products. All right. So characteristic set means the set where this is 0. Okay. Well, this is complex valued. So this is 0 if and only if the following, the real part has to be 0. The real part is tau plus a real part of a of 0 inner product C. So this has to be 0. And the imaginary part has to be 0. Imaginary a of 0 dot c has to be 0. The imaginary part of a of 0, remember we said it was minus imaginary part of phi of 0. So this is the same as saying this thing. Okay? So a vector c tau, a non-zero vector. So we always take a non-zero vector. A non-zero vector is in the characteristic set of L if c tau satisfies this pair of equations. And what I'm saying is, if something is not in the characteristic set, then if you have a solution, then that thing is not in the wavefront set of F. That's what I'm trying to prove. Okay? Only one more step. We are done. We have done the difficult, almost everything. So first, notice the following. You see that these two terms are appearing over here. You see, so there is tau and c dot real part of a of 0. Why is it plus? Maybe I think I made a mistake here. Maybe this is plus. And we have imaginary phi of 0 dot c is here. So look, this holds. So let me call this condition A. Or this doesn't hold. This doesn't hold means one of the terms is not 0. Either this is not 0 or this is not 0. Well, that means that either this coefficient is not 0 or this coefficient is not 0. In that case, you can find a theta. You can find a theta, some theta, such that this sum is not 0, right? Because you see, this is not 0 or this is not 0. If one of them is not 0, then this vector, the vector where the first component is this number, the second component is this number, that vector is non-zero. If that vector is non-zero, then you can find, cos theta, comma sine theta, so that the inner product is not 0. Conversely, if this is not 0, then either this part is not 0 or this term is not 0. Which means either this one is not 0 or this one is not 0. Which means that these equations are not valid, which means c comma tau is not in the characteristic set. Okay, is that clear? So let me call this condition A. Yeah. So and this condition B. So this c tau is not in the characteristic set of L at the origin, if and only if, okay? If and only if this is not 0, which means this is not 0. If and only if c tau, the imaginary phi theta, 0, 0, is not 0 for some theta. So if and only if there exists theta such that this is not 0. Okay? All right. Well, let's look at the lemma. The lemma said that the lemma applied in the previous lemma, applied to the vector field L, said that if this thing, if imaginary phi, there was a sign condition in the lemma, right? If this is negative, then then C naught is not in the characteristic, is not in the wavefront set of the trace of f, the trace of f, okay? All right, two things. First of all, for trace, so my solution was f of xt, right? So let me define this function of the three variables to be just f of xt. Then, first of all, for all theta, L theta f tilde xts, L theta is like L. It just adds one more differentiation. It has d by ds. But d by ds, I mean, doesn't act on this. This is a function of x and t. So this is the same as LF, and by hypothesis, this is 0. Great. 1. 2. Two. Okay, so I want to apply this result to L theta now, okay? Except that here I had a condition, imaginary field was negative. But now what I have is, all I know is it's non-zero. It could be positive. Well, if it is positive, if I change theta by minus theta, this will be negative, okay? Okay, not by minus theta, by pi minus theta, okay? If it's positive, okay? So change by theta. So if c tau, right? If you put sine of pi minus theta is minus sine theta, cos of pi minus theta is minus cos theta, right? So you see, so if this happens to be positive, use instead of theta pi minus theta, okay, or theta minus pi. And so therefore, this condition is also satisfied. So by the lemma, what do we conclude? The trace of this at s equal to 0, which means f. For f, the vector c naught 0, c tau is not in the wavefront set. Okay? So therefore, by the lemma, in other words, this by the lemma, c tau is not in the wavefront set of f. And that therefore the wavefront set of f, I have proved for you that the wavefront set of f is contained in the characteristic set of L. Because if something is not in the characteristic set, then it's not in here, which means f microlocally is nice. I proved it for C infinity, but real analytic, exactly the same result, the same proof. Because in the real analytic case, you can get those zj and so on, as I said, okay? So if you study regularity of, say, CR functions, which are, you know, they are functions which are solutions of a system of equations, except unlike the D bar, this system is not elliptic. So they are a good model for non-elliptic system of vector fields, okay? So that's what, so I want to conclude with a description of a problem you can work on, okay? And I think it's tractable. So the situation is the following. So first of all, so this is a general fact, general. So suppose you are given a system of vector fields, say Ln, okay, they can be CR or they may not be CR. So these are just linearly independent vector fields. Okay. And you have a solution, Lj equal to 0, okay? Okay. These don't have to have these solutions Zj and so on. They don't have. They will always have approximate solutions. Okay, so these are general. Then what we have shown actually shows that. So then, the wavefront set of a solution is contained in the intersection of the characteristic sets of this. Okay. Now in the CR case, what makes the CR special is that the characteristic set in general could be a bad set with no structure, may not be a manifold and so on, okay? But in the CR case, it is a manifold, it turns out to be, okay? All right, now, so therefore, you see, one is interested in when something that is not in the characteristic set is not in the wavefront set of a solution, okay? Now, there is one case, specific case of vector fields called tube vector fields, Okay, so you have n vector fields, L1 up to n, and you have functions zj of xt equals xj plus root minus 1 phi j that depend only on t. That's why they are called tube vector fields for j 1 up to m. Here, x is in Rm, n is in Rn, not n, t is in Rn. Okay? So there are, these vector fields are the vector fields that form a, that actually kill this. Okay? And so they can be written as Lj is d by dtj plus, I will have to spend a minute or so to remember them, but they're something like this. Okay? You can find them in our book. They are something like this. Okay? For these kinds of vector fields, the regularity has been studied by several people. Okay? In particular, when the vector fields are real analytic, the regularity is well understood. Namely, I mean, one knows exactly when all solutions are real analytic. Okay? Even microlocally real analytic. Okay? And so, so you take this. Suppose you have a solution, Lju equals 0. U can be a distribution solution, j less than or equal to n. The question is, if I give you a certain direction, say, when is this not in the wavefront set of U? Okay, if the Lj are C infinity. And when is it not in the real analytic wavefront set of U? Okay, similar question, okay, in the analytic case. So let me tell you that in the analytic case, there is a very nice, simple, necessary, and sufficient condition, the analytic case. Okay? So this is due to Boundy and Treves. Okay? I think I sent this paper to Florian, I believe. Okay? It's the simplest papers I have ever written. Very simple to understand. Okay? So the only thing is in there is Stokes theorem, but using the DZJ, exactly the way I showed you. The way I showed you. Okay? So whatever I showed you should be enough to read that. Okay? There is only one deep fact they use. Okay? They use, and that's something from, there is something called Hironaka's theorem. From the, but in a paper that I wrote, that you will see, even that part, there is a simpler version. Okay? Indicates that there is a, you don't have to use Hironaka's theorem. Anyways, in this case, here is what they showed. Consider the function t going to C naught inner product phi of t. Okay, so you see there are m of the phis. So phi means phi 1, phi 2. Okay, so C naught is a vector in Rm. Consider this function. In all this, you may assume that phi at 0 is 0. Okay. So at 0, this is 0. And then there is a question of, so here is T space. And sometimes at 0, this has a local maximum, weak maximum. Sometimes it might have local minimum at 0, this function. Okay. Now, if this function, so for all solutions, U, it turns out that in fact 0 C naught is not in the real analytic wavefront set, real analytic I'm talking about, of the trace of the solution, if and only if this function does not attain a local extremum, a local maximum or a local minimum. You understand that? Which is a very simple condition to check, right? Does not attain a local extremum at 0. This is in the real analytic case, okay? Okay, now in the C infinity case, this condition, it's easy to show, is a necessary condition always. And for some time after they wrote their paper, people tried to see if it was also sufficient. Then somebody showed in a short paper that in C2, there is a CR vector field which satisfies this necessary condition, but the regularity is not true. So in the C infinity case, in general, it's not true. And so therefore one tries to find sufficient conditions that imply regularity when phi is infinite, okay? So this part is when phi is real analytic, okay? So when phi is infinity, partial, so boundary intercepts in that paper, the main object, the main result is really, in the infinite case, they prove some sufficient condition expressed in terms of the function phi, and then I generalized that sufficient condition, okay? But there is a lot of room, and so your problem will be to find other classes of functions phi for which these results, boundary intercepts, and my result can be generalized, okay? You don't have to know a lot, okay? Now, in the boundary and the Treves case, let me mention their generalization in the, the way they got infinity result was by assuming some quadratic condition on phi, quadratic condition in the FBI, quadratic condition in the phase of the exponent of the FBI, okay? It was quadratic because the FBI itself is quadratic. But then George Hooney and I, we generalized the FBI, where instead of taking quadratic, one can take any polynomial, okay? And that's what I used to be able to generalize theirs, okay? Then I had to, the problem I had to study was given any polynomial, homogeneous polynomial, in Rn, to try and estimate what its minimum can be. Not any polynomial with, I think, positive coefficients, something like that, okay? And I was working on that, and then you've heard of the first book on tech, AMS Tech, written by Knuth. In any case, he had written a book on computer programming, and one of the exercises in that computer programming was this. was trying to find a minimum for the kind of polynomials I was looking at. Okay? Well, in any case, eventually then, I found papers, thanks to Google. These people that study, what's called geometric programming, blah, blah. There are these people that estimate polynomials. People in algebraic, real algebraic geometry also do that. And I was able to use their results to generalize, okay? And so you might be able to do a similar thing also, okay? Now, in conclusion, I want to thank SIMPA, and I want to express my special gratitude to Florian for making this possible. AUB has a special place in my heart, because for most of you don't know, but my father studied here. Not math, but he studied here. History, okay? And so the first time I came here was in 2017. I came with my daughter to show where her grandfather studied. And we loved it very much. And AUB, I'm also very grateful to AUB, because for many years, in my former university, Temple, I was a graduate program director, and we got the best students from AUB. In fact, as a testimony to that, 2 of the current professors are our graduates from Temple. And we had some other graduates also. One, I had a student who is a professor in Abu Dhabi. And there was another very, very talented person, Abed, very talented, but a person devoid of any ambition, zero ambition. I don't know where he is, what he is doing. Extreme talent. But let me tell you how Abed joined the Temple. I was teaching a summer course, preparing students for these PhD qualifying exams. Okay? And just before that, Abed stopped by my office, and he said he wants to apply. And I said, where are you from, blah, 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 and what courses did you take at AUB? And then I said, why don't you come to this class that I'm teaching? And then I was in that class, and then I asked the students some question. None of them could answer it. Abed answered it, and then I told him, you are admitted. And he wrote a fantastic thesis. He published 4 papers from his thesis. Then he disappeared. I don't know where he is. So thank you very much. Abed, I don't remember his last name, but I'm sure people in AUB will remember.
In any case, now that you are in Maryland, we still count on you for the if you have a very good student, sure, send them. Yeah, definitely. And if you invite me, I'll be very happy to come again too. So thank you very much.